Hi, everybody. It is June 3rd. Excuse me. Can we please take our seats? Thank you. Thank you. Hi, everybody. It's June 3rd, and we're going to be wrapping up our nuclear chemistry unit with a lesson on what is half-life and how can radioisotopes be used by humans in addition to generating electricity by fission reactions. Okay, so let's start with half-life. By definition, half-life is the time it takes for 1/2 of the atoms of a radionuclide to decay. And the shorter the half-life, the less stable the radionuclide. So we can look at, as a reminder, we have our radioisotopes or radionuclides all listed here. We have milliseconds, calcium 37. That is a really short half-life. It is very unstable. Let's look at technetium 99 as an example. This decay graph, and this graph can represent any radioisotope. Of course, what's going to change is the T1/2, that's the half-life. Using technetium as an example, the half-life is 6 hours. So you're always going to have in these graphs the fraction of sample remaining. So you're starting with the whole amount, whatever amount you begin with. And every time, so if we start with 100% of technetium, whatever amount that is, in 6 hours' time, we are going to have half of that amount remaining. Another 6 hours pass, and we end up with 1/4, then 1/8 of the original amount. Let's look at some examples of half-life problems that you can encounter. So our first example, how much technetium 99 will remain after 18 hours when the starting amount is 500 grams? So imagine we're here, we're starting with 500 grams. After 18 hours, how many grams will remain? In my opinion, the easiest way to work through half-life problems is to make it very visual. So if I start with 500 grams of technetium, I know after one half-life, I'm going to have half this amount, 250 grams. Now, you will always be provided with the half-life in a question, or it's going to show up in table N. In this example here, the half-life is 6 hours. They want to know after 18 hours. Well, we have to have another 6 hours go by. After another 6 hours, we're going to have 125 grams. We're going to have another 6 hours go by. And then we're going to have 62.5 grams. I recommend that you set up your half-life problems like this. You're not going to be very likely to make mistakes if you do this. You're always going to write the half-life, T1/2, up above the arrows. You're going to show the initial mass, then the subsequent masses after that. Notice this is the fraction. This is 1/2 of the original. This is 1/4 of the original. This is 1/8 of the original. And it could keep going on. So our answer here is how much? 62.5 grams is how much. How many half-lives have occurred in this example? 1, 2, 3 half-lives. Let's look at another example. So now they're asking how many days are required for 200 grams of radon-222 to decay to 50 grams. If we look at table N, radon-222 has a half-life of 3.823 days. So we're starting with our 200 grams. We know we have 3.823 days, and that will bring down the sample size to 100 grams. We want to get it to 50 grams, and we'll be able to stop here. But let's write our days up there, 3.823 days. You're noticing there's 2 half-lives represented. When we add up these 2 half-life time periods, we end up with 7.646 days. Let's look at a third example. After 32 days, 5 milligrams of an 80 milligram sample of a radioactive isotope remains unchanged. What is the half-life of this element? We don't even know what element it is, but we can work this out. We know that we're starting with 80 milligrams of some substance X. After 32 days, there's 5 milligrams left. Well, how many half-lives will it take to get to 5 milligrams? Let's just keep doing this. 80 goes down to 40. 40 goes down to 20. 20 goes down to 10. 10 goes down to 5. Okay, we could stop there. Oops, milligrams. Sorry, folks. All right. So how many half-lives have occurred? 1, 2, 3, 4. That's 4 half-lives. What is the half-life amount, though? Well, if the whole amount of time is 32 days, there are 8 days, because 8 times 4 is 32. This must be an 8-day half-life. So we take the duration of these decays and divide it by the number of half-lives, and we end up with 8 days. Okay, we're going to switch gears a little bit to our second question for this lesson, and that is, how can we make use of radioisotopes? So yesterday we learned that isotopes can be used, in particular uranium, as a fissionable material to generate electricity. Let's see how radioisotopes can aid in medicine. So we would call this branch of medicine nuclear medicine or radiotherapy. And radioisotopes can provide information on the functioning of an organ, so it's going to help in the diagnosis of a disease, or they could actually be used to treat a disease. And the key thing to note is that radioisotopes with short half-lives are preferred because they minimize the radiation dose to patients. So, there are risks associated with radiotherapy. We are actually exposing humans to radioactive materials, but the benefits outweigh those risks, and there's a careful planning of the type of radioisotopes to use. So I'm about to give you a general idea of how radioisotopes could be used in radiotherapy, okay? So a radioactive dose of some isotope is given to the patient. These are known as tracers because medical professionals can trace the emitted radiation as these particles decay, and they can trace where those emissions are found in the human body. How? Well, the radioisotopes are linked to a compound that is naturally interactive with the organ of interest. So if we link that to a compound that's naturally going to be found in the body, it's going to give us a picture using technology. It'll give us a picture of what's happening inside the body. These radioisotopes could be injected, inhaled, or consumed orally. And ultimately, what ends up happening is there's organ imaging that occurs, which permits a view of the radiation emitted and allows visualization of any abnormalities. Some techniques would be PET scans. These are positron emission tomography techniques. You might have heard of this too. CT scans, computed X-ray tomography. These techniques are using radioactive isotopes to aid in human health. There are many examples of radioactive isotopes that can be used in the medical field. These are some. Iodine-131 can be used to diagnose thyroid disorders. It could also be used to treat thyroid cancer. Phosphorus-32. This can be used to control excess red blood cells that form in the bone marrow. Iridium-92. This particular radioisotope is very useful to control head or breast cancers. And to conclude this lesson, I want to remind you that there are many uses of radioisotopes. One is carbon-14 dating. And if you took earth science, you have spent some time studying this already. If you haven't taken earth science, you should. You'll learn some interesting things. But carbon-14 dating can be used for dating the age of organic materials that are derived from once living organisms. I hope you enjoyed this nuclear chemistry unit. We have finished. Have a wonderful day, folks. Bye.